All right. So I'm live right now. So I said that I would, because of a test and such, I would split up today's lesson in two halves. So the first half would have a discussion of the anti-derivatives, because we started that, and I don't want to lose that. It's kind of one of the things that's really important. It's not going to be on this test because unfortunately we just covered it right before the test, so it wouldn't be fair to to kind of you learn it this week and it's on the test right away. And we already have a lot of stuff that we need to focus on this second test. But this is important because it really gives you the passage to the last part of the material, to integrals and all that. And that's very important. Integrals so there's three important things here. So the first thing is limits, which with tables and things like that, you can kind of get away with those without doing a lot of a lot of complicated stuff. But derivatives already, it's a place where you need to spend a lot of invest a lot of focus, in energy, and I want you to do that. That's the purpose of the first the second test and the second quiz. So that's really covering the derivatives, those derivatives, focus on those. And then the third part is the part that we just started, anti-derivatives and integrals. So it's really, this is the bread and butter of integrals. So if you don't know anti-derivatives, you're going to have a really hard time getting through the last part of the semester. However, if you know this, you will have a really easy time, because everything we'll do afterwards, we'll just learn about some small technicalities, Riemann sums, things like that. So those, can be forgotten, and you can still do fine in calculus. But without anti-derivatives, again, that's one of those things you don't want to do, not learn the anti-derivatives. All right. So today's lesson, the first half, will do yet a more review of anti-derivatives. So it's kind of a third lesson when we spend time on that. So I really want to make sure that. So if you come here, if you've heard that 3 times, I believe that you actually are going to get it. If you watch at home, you haven't been here, so please watch the previous 2 lessons as well. And make sure that you understand these all three, they're kind of like just three petals of the same flower, so it's kind of, it's the parts of the whole, and you cannot they kind of skip this. It's not a good idea. All right. So that being said, I'm gonna do this, and then to the second half of the hour, I'm gonna essentially take questions. So we don't have to. I'm thinking that we don't even have to record that. I'll just take questions from you, and I will kind of point out some review topics, or maybe I don't know. So maybe we'll decide what we do in the second half. Um, but right now, let's get started with. If you have questions, folks, keep asking. Again, I noticed a couple of a week ago or so, I had a little bit of a technical problem here, and I remember I even got disconnected. So if you see that something is not working properly, my voice is breaking down or something like that, so do contact me quickly so I can resolve that here, and I don't have to kind of talk to myself here, and if the thing doesn't work. All right. So that being said, okay, so I'm going to share this with you folks. All right. So this is going to be so we continue 3.9, and that's going to be anti-derivatives. And I'm going to say continued here. And if you remember what we did last time, so we did this. So we said, okay, so here's the antiderivatives. We derive some formulas, right? Remember that the antiderivative in theory, it's a very simple definition. It's very easy to understand. So if I say that, let's say capital F prime equals F, so the derivative of F prime is, of F, of capital F is lowercase f, then I can say in words that the antiderivative of lowercase f is capital F. So I can say that in words. All right, now there is a symbol, I told you there is a symbol for the antiderivative, but the book wisely does not introduce that so that people can kind of get used to the concept, thinking of the concept and not getting bugged by that symbol, because that symbol, tends to confuse a lot of people. So you will see later on in the semester, the symbol is not particularly simple, and it tends to confuse a lot of people. Some folks, some books even simplify that symbol, so it's called integral dx or something like that. So they drop a dx just to kind of place forward this idea of working with an antiderivative, not just just a bunch of symbols there that confuse people, for historical reasons. There's some other reasons, they're kept there, but so you have to understand the concept before you get to the symbol. All right. So last time we did some formulas, and I'm going to review those formulas quickly. So formulas. So the antiderivative, first of all, the most important is this one, the antiderivative of x to the n is 1 over n plus 1 times x to the n plus 1. So this is a very important formula here, folks. They're very, very important. So nobody will believe that you pass calculus if you don't remember this particular formula, because this is like, kind of so likewise, the formulas for derivative, the derivative of x to the n being n, x to the n minus first. These are some very, very super basic formulas that should be in your bag of tools every single day after this class is over. So and what during this class as well. So everybody should really focus on making sure that they oops. Okay, folks, I don't know what happened here. So I misspelled. I'm sorry. I just noticed I misspelled the antiderivative. That's weird. All right, so let me write that again. Antiderivative. There we go. Antiderivative. So of x to the n is that. All right. So so this is something that you really, really need to know. That's one thing. And then for the trig functions, I told you that there's 3 trig functions that are more important here. In fact, it's really 2. So the antiderivative of sine, remember how that is negative cosine x. So you can check yourself that the derivative of negative cosine x gives you sine x. The derivative of cosine x is sine x. All right, so this is 1 there. And finally, the antiderivative, and this, this is important, but I would be a little careful here because it's not in the same league as these other two, and people usually don't use secant squared in calculus too. So in calculus you'll hear something different, and that's so rather than worrying about those technicalities, which it's more or less the job of a calculus 2 instructor, I'm just going to say the antiderivative of secant squared x is tangent x, and I'm going to leave it at that because that's what they leave it at that in the book. So in the book they don't worry about 1 plus tangent squared and things like that. So that's what secant squared is, 1 plus tangent squared. But again, in calculus 2, you will hear a slightly different formula here. So you know, kind of be aware that this third formula that I put here, it's going to look a little different in, well, maybe significantly different in Calculus 3, in Calculus 2, I'm sorry, if you take that class. So these are the basic formulas, and this is what I wanted to review here. I want to make sure that everybody understands how important these are. Of course, you can add a constant c. We discussed about the importance of adding a constant, and we will see a problem today where it's very important to make sure that you add that constant properly. So, so that is our first part here. So reviewing this. Now, last time we did some examples. So how do you combine these antiderivative? Well, the good thing about them is that it's very much linear in a way that is, you know, you take constants out if you have a constant factor and so on and so forth. So the sums, you split them up, but these are the basic ones. So, so you can do other things, but these are the basic ones. And what I'm going to do here, folks, I am going to do slightly more sophisticated examples. So I'm going to start with problem 7. All right, folks. So let me take this out of the way. It's always in the way here on my screen. So so problem 7 of section 3.9 is f of x here is equal to 7x to the 2/5. Whether is it 2 or 7? Oh boy, my eyes aren't very good anymore. So 7x to the 2/5. All right, plus 8x to the negative 4/5. Okay, so so there we go. We could have any other numbers, doesn't really matter. So we want to find an antiderivative here. Okay, so let me delete that. Okay, antiderivative, folks. How does that go? Well, here's how that goes, folks. So over here, we will say, you know, for the first one here is going to be 7 times the antiderivative of x to the 2/5. What is the antiderivative of x to the 2/5? Is x to the 7/5. Why is that? Because it's, remember, folks, here, this guy here, maybe I shouldn't write it 2/5. I shouldn't write 7/5. I should write 2/5 plus 1. There we go. So everybody can see it, but that's 7/5, right? This guy here. And then 1 over that thing, because remember it's 1 over, so x to the n plus 1 and 1 over n plus 1 in front of that. So here's the formula here, right? This formula, so this exponent n plus 1 at the bottom. So so I'm going to put here 2/5 plus 1. Again, in practice, I don't do that. I don't recommend that you do that. So just write whatever this sum is here, 2/5 plus 1. And then you'll say plus 8 times, and the same story over here. Let's leave some room to complete the constant at the end, but the exponent here will be negative 4/5 plus 1. And the constant here, the coefficient will be 1 over negative 4/5 plus 1. So so this is the antiderivative, and then we can say at the end, if you know, if you fancy a constant, you can put a constant there, so plus a constant. All right, so we need to simplify a little bit this result, and by the way, folks, one of the disadvantages, and I know there's software out there that calculates antiderivatives, but they do give the result simplified, and that's a problem because many of these pieces of software don't really know how to do this algebra properly. But a lot of them know, but there's software out there, and I tried one that I can point you out to that website. I tried one, and I could see that it doesn't know how to do these very well. So 7 times 1 over, and this is the type of calculation that you want to do. And you want to show on the test maybe. So 2/5 plus 1 is going to be 7/5. So 1 over 7/5 times x to the 7/5 here plus and then there's 8 times and 1 over here, negative 4/5 plus 1 is 1/5 times x to the, and the same story at the top here, negative 4/5 plus 1, which is 1/5. So this is going to be equal to plus a constant, right, plus c. And this is going to be equal to, by the way, folks, to 7 times 1 over 7/5 is 7 times 5/7 times x to the 7/5 plus 8 times 5, right? 1 over 1/5 is 5 times x to the 1/5 plus c. So this is going to be 5 times x to the 7/5 plus 40 times x to the 1/5 plus c plus a constant. So this is going to be the final result, folks. This one that I wrote here, 5x to the 7/5 plus 40 times x to the 1/5 plus c. All right, so this is the antiderivative. So the derivative that we have right now, the next antiderivative, I'm sorry, folks, if you want, you can calculate the derivative of this one, and you will see how you get exactly the function we started with, and this is a good way to check that your results are correct. For instance, 5 times the derivative of x to the 7/5 is going to be 5 times 7/5 times x to the 2/5. So 5 times 7/5 will simplify to 7. And now we get 7x to the 2/5. And then the next thing is 8 times, over here. So the next thing is 40 times 1/5, which turns out to be 8, times x to the 1/5 minus 1 when you calculate the derivative. And that's going to give you x to the negative 4/5. So this is the result that is doing that. All right, so this thing here, folks, is exactly what we need for the antiderivative. So let's do one more example. I'm gonna, as I said, this first half hour, I'm gonna do a bunch more examples. And the next one is number 11 from the section here, from 3.9. F of x is 3 square root of x minus 2 cube root of x. All right, so we haven't seen many of these, the way things go here, we don't really get to use really in practice, folks, cube root and things like that, higher roots of x. I more or less avoided putting some of those on tests and such, because if I believe that square roots, that's going to be good enough. In physics and other classes, I don't think you will use anything like cube roots. So these square roots would be fine. But this is a good example to see how things work in a little more general context, because, if you end up in calculus 2, maybe not even that, maybe in calculus 3, or some, advanced calculus or some class like that, then you would certainly need to work with more elaborate radicals like this one here. So in this case, what I'm going to do, first step is to rewrite my problem as a bunch of powers of x. Again, there's no hope to do antiderivatives of radicals and things like that directly, because there's no formula for them. So the way to do that is to write them as powers of x and interpret the problem as we did in the first part, where the exponent here is maybe a fractional exponent, exactly like we did in the problem earlier, where we had 2/5, negative 4/5 and such. So over here we have 3x to the 1/2, because that's what square root of x is, minus 2 times x to the 1/3. So remember, folks, that the cube root of a number is that number to the 1/3. All right, so that being said, after you pay attention to this thing, you can certainly do antiderivative. So antiderivative, folks, is for 3x to the 1/2, I'm going to say 3 times. And remember that for the antiderivative, it's easier to figure out the new exponent which is going to be 1/2 plus 1. Now we're big kids here, so we can do that in our head, right? 1/2 plus 1 is 3/2 here. All right, folks. And what I would have here, I would have 1 over 3/2. But doing 1 over a fraction is the same as flipping the fraction. So I'm just going to say 2/3 instead of 1 over 3/2 minus 2 times, and then the cube root of x, which is x to the 1/3 here. So I'm looking at that. So x to the 1/3, okay, so that's going to be x to the 4/3 times, and then it's going to be 1 over 4/3, which is going to be 3/4. All right, plus a constant c. So this is the situation that we're looking at. So this is the final result, and we can easily, now simplify some stuff here, the 2 and that, so we will get the final result is 2x to the 3/2 minus 3/2 x to the 4/3. Now in the book, they sometimes, for whatever reason, they like to kind of confuse you and write this answer back in terms of radicals. You could, if you wanted to, the exact same thing is 2 square root of x cubed, that's x to the 3/2. So remember, refresh your college algebra or pre-calculus if you don't remember that. Minus, and over here, that's 3/2 square. Well, what kind of root? Actually, this is going to be a cube root of x to the 4. If so, again, remember, refresh. You might want to refresh your college algebra for that. And this turns out to be, and it can be simplified a little more. Now, remember that when you do the square root of x cubed, you can write x cubed as x squared times x, and that's going to be 2x square root of x. And the other one is negative 3/2 times. And over here, cube root of x to the 4, the same logic, x to the 4 is x cubed times x. So that's going to be x cubed, cube root of x cubed is x, and that's going to be x cube root of x plus the constant c. So in the book, they sometimes write the answers like this. Again, they're not trying to confuse you. They're just trying to make sure, folks. So I was joking when I said they're trying to confuse you. Try to make sure that you really know your algebra well. Now on the test, I'm not going to be that picky about these answers. So in fact, you saw how my test will give you a bunch of selections. First, I also expect you to show work, as you remember that I expect you to take a picture of your page and show work. So it's okay if you guess the answer. It's okay if you guess the answer for by some I don't know, some intricate method, but you gotta show me that method. So if you can show me your work and how you relate your work to the final result, I'm not gonna give you a lot of points there. So there is a little bit of points for guessing, but not a lot of them. All right, folks. And finally, I'm going to do something that is a little more sophisticated. So I'm going to do 2 more problems, and then we'll move on and we'll do one that really uses the constant c, because up to this point, you haven't seen how to use that constant c. So my next problem will be number 13. Again, folks, these are, by the way, these are homework problems. So again, when you go home and you do the homework problems, look here, stop the video, do the problems yourself, and then check how they're done here. So number 13 from 3.9. All right, so we do f of x equals 10 divided by x to the 9. And we want an antiderivative. And like we said, there is no such a thing as a product rule or a quotient rule or so we can safely say that there's no such a thing for antiderivatives. And what do? Well, so the thing that you do is you rewrite this thing and you try to write it as a power of x. And it turns out that that's not so hard. 10x to the negative 9, that's the answer here. So that is that's not the answer to the problem. That's the rewriting of this question, folks. I still have to do the antiderivative of this, which is much easier than the one I started with. And the antiderivative is going to be 10 times, and let's be careful here, x to the negative 9 plus 1, folks, is going to be, I'm going to write it that way so everybody can see x to the negative 9 plus 1 and 1 over negative 9 plus 1, because that's the formula, right? When I do the antiderivative of x to the negative 9, I get that. And this is 10 times 1 over 8, 1 over negative 8, I'm sorry, x to the negative 8 here. So that is the answer. So it's misleading because you could think, oh, negative 9 plus, maybe it's negative 10. No, negative 10 is not. That would be minus 1, right? So be careful here, folks. The answer, the final answer is, I'm sorry, not 10. So let's simplify. 10 divided by negative 8 is negative 5/4 times x to the negative 8 plus a constant c, right? So that will be the final answer for this problem. All right, one more problem, and then we'll move on to something slightly different. So I'll do this. This is the type of complicated problem that it might show up. So we'll do more when we move on. So we'll do yet another problem like this when we get closer to the next quiz and test. So number 15 of 3.9 says the following thing: take this function f of x equals, and now it's a fraction, square root of t, 1 plus t plus t squared. Now let's look at the previous fraction, because we had a previous fraction there. So why is that thing here? All right, so there was something there. All right, so let's take a look at the previous fraction. What did we do with that? Well, we wrote it as a negative exponent. I will do the exact same thing here. So I'm going to say the top part stays the way it is, 1 plus t squared times, and over the square root of t is times t to the negative 1/2. So this is what it means, dividing something by the square root of t. It means multiplying by t to the, square root is 1/2, but because it was at the bottom, it's negative 1/2. All right, and this function is equal to t to the negative 1/2 plus t to the 1/2 plus t to the 2 minus, by the way, folks, how do I multiply? Well, I multiply term by term, distribute, right? So 1 times t to the negative 1/2 is that. T times t to the negative 1/2 is t to the 1 minus 1/2, because this is t to the first power here. T to the 1 minus 1/2 is going to be 1/2, and t to the squared minus 1/2 times t to the negative 1/2 is t to the 2 minus 1/2, which is 3/2. All right. So this is the polynomial. And you know what? I wrote f of x. Why did I write f of x? Should be f of t. Sorry about that, folks. So I lost focus here. So this is my function f rewritten. So I didn't do anything intelligent. I just wrote it as a sum of powers of x, folks. Now comes the clever part. So when I do the antiderivative, all right, so when I do the antiderivative, I get t to the, so for negative 1/2 plus 1. So that's going to be 1/2 plus t to the, now over here, what do I have in front of t to the 1/2? I have 1 over 1/2. Now, if you're careful here, that really boils down to being 2. Okay, the next thing will be t to the 1/2 plus 1. It's going to be 3/2. And I'm going to say here 1 over 3/2 over here. So by the way, let me write that with a fraction here. So let's write, instead of that, let's write the fraction nicely. 1 over 1/2, 1 over 3/2 here. All right, and the next thing is t to the 5/2. And I'll do 1 over 5/2. And this is the new thing, plus a constant c. And that, folks, becomes 1 over 1/2 becomes 2 times t to the 1/2 plus 2/3 times t to the 3/2, right? To invert, flip over 3/2 there, plus 2/5 times t to the 5/2. So you see, folks, this is my lovely antiderivative. I forgot to say plus a constant. Let's add a constant c here. Plus a constant c. All right, so this is my lovely antiderivative, which is derived based on the sum that we have there. And because I said this and I didn't do an example with trig functions, let's do one. This was not an assigned problem, but I'm thinking it might be a good idea to do this instead of the one that I was planning. So let's do this one, folks. This is number 15. I'm done with that. So let's do number 20. I think number 20 is a good problem for you to practice as well at home. So, so number 20 of 3, 9. The function here is f of x equals 1 plus 2 sine x plus 3 divided by the square root of x. So, so this is the function, and I am going to do the antiderivative. I'm going to do the antiderivative of that, but before I do it, again, I need to write something nice here. So 1 and 2 sine x are fine. You know, are functions that I am familiar with, but 3 over square root of x, not good. So I'm going to write instead of that 3x to the negative 1/2. And right now I am fine. So I can do the antiderivative again of this expression, which is just rewriting the function f. So again, with just rewriting the function, folks, I give partial credit for problems. So just rewrite that so I see that you really understand what you need to do there. All right, then the antiderivative is the following. For 1, the antiderivative is x. X prime is 1, right? So we all know that. Or you could say because 1 is x to the 0, the antiderivative will be x to the 0 plus 1, 1 over 0 plus 1, and that turns out to be x. But, you know, you don't have to worry about that formula because in this case, things are pretty straightforward. For 2 sine x, I put a plus, but as soon as I put the plus, I realized it's a mistake, so it should be minus 2 cosine x. Why is that? Because the derivative of 2 sine x is, of sine x is negative cosine x, and you multiply by 2, you get that. All right, plus, and maybe I need to put something here too. Let's see. So it's 3 already because it's there. X to the negative 1/2. When I do the antiderivative, I get x to the negative 1/2 plus 1, which is 1/2, and that is just fine. And then we would say 1 over 1/2. Now remember that this really is 2. So plus a constant here. So I'm going to say the final answer is x minus 2 cosine x plus 3 times 2, which is plus 6, x to the 1/2 plus c. So this is the antiderivative. All right. Now, this antiderivative, folks, is one of those things that I like this kind of problem. So so let's be honest, I like that. I would put these kind of things in, and you should expect these kind of things on the coming quizzes, the quiz and test and final. So it's going to be quiz 3, test 3, and final. Not on this one here because again we don't do antiderivatives on this quiz. So let's do one more problem, and since I spend my time doing these antiderivatives, I'm not going to move any further in this with this lesson. I was planning to do something else in the second half, but you know, for the time being, let's just stop here with this problem. So here's a problem that you might want to look at, and over here in the book it says, you know what? Let's do this problem here. So that's number 32. And again, I put problems like these on test, so be careful there. So 3.9, and this says that f prime of t, so you know the derivative of a function, and that is 1 plus 1 over t cubed. And you also know that t is greater than 0, and you also know that f of 1 is 6. For the time being, this is not so particularly important as much as it only tells me that I can calculate the antiderivative properly, because if I have to go through 0 at 0, some things happen. So for practical purposes, you can actually erase this part here. So the important part for us here is just this one and this one. So we know that f prime is that. We know that f of 1 is that. Find f, it says in the problem. Now, where do I see problems like these? Because, so there's a reason why I'm doing this kind of problem, folks. You see problems like these in physics. So when you estimate the movement of some object, you know, sometimes the displacement, sometimes the way, so if you took a physics class, or you will take a physics class, you will see that the way they derive the fact that the motion in space, in 2D, right, in 3D, let's say. So if you throw a rock, you know, it's describing an equation that can be easily calculated. The trajectory can be shown to be a parabola. How did they do that? Well, here's how they do it in physics. So now I'm not sure that all physics classes teach that, because there's physics for physics with college algebra and physics with calculus. So I'm assuming that this would be in a physics with calculus class. But the way they would do that, they would say, you know what? The second derivative of a displacement function is, the first derivative is velocity, and the second derivative is the acceleration. But when I throw a rock in the air, you know, I just throw a rock from here to there. I want to hit a tree or something. So what happens is, the rock is the initial velocity, the push that I give the rock at the beginning is important. So that's the initial velocity. But the key component of the trajectory is actually determined by the acceleration, and the acceleration is fortunately known. So in physics, because the only force that acts on my rock after it leaves my hand is the Earth's gravity. So gravity is the acceleration, and that can be calculated. So people know what the value of gravity is 10 meters per second squared, approximately, or 32 feet per second squared. So we know the gravity, and because we know the gravity, we know the second derivative, and then we go backwards and we find the first derivative, which is the antiderivative of the second derivative. And then once we know the first derivative, we find the equation of a trajectory, which is the antiderivative of the first derivative. So, so this is where these type of problems are important. Right now, we're doing a simple problem. So first of all, let's realize that f prime. So let's go back to our problem. I gave you the big context. So f prime here of t is equal to 1 plus t to the negative 3. So f of 1 is equal to 6. The function that I'm looking for, f, is an antiderivative by definition, right? The definition is that if the derivative is 1 plus t to the negative 2, this is an antiderivative of 1 plus t to the negative 3. So it's very easy to say what f will be. F will be the antiderivative of 1 is t, and the antiderivative of t to the negative 3 will be t to... all right, folks, sorry about that. Not writing properly. T, what's wrong with this? T to the negative 2, and then over here I would have 1 over negative 2. So that would be my antiderivative. So let's say for a second that this is t minus 1/2 t to the negative 2. would we be able to see that, to say that this is our function? So remember, no, because if we calculate f of 1, we will see that f of 1 is 1 minus 1/2 times 1. 1 minus 1 minus 1/2 is not good. F of 1 has to be 6. So here's the trick, folks. We need that constant c. That's going to be the trick here. So when we calculate f of 1, if we want that to be 6, just remember that this is 1 minus 1/2 plus c, and we want that to be 6. And then c is 6 minus 1/2, which is 6 minus 1/2 is 12 minus 1/2 is 11/2. All right, folks. So c is 11/2. That's how you find the constant c. And our function, our answer is, folks, this is how they get the answer in the book. F of t equals t minus 1/2 t to the negative 2 plus, and the constant c is very specialized, is this one, 11/2. So remember, folks, the constants, these constants are representing in physics the initial velocity or the initial displacement, for example, depending on the situation that you work with there. So they are very important. These are very important, these initial constants. Now, fortunately or unfortunately for us, we will not use this type of problems anymore after this one lesson. So fortunately, all the antiderivatives that we use in the future could be defined vaguely. So you could drop that constant c and no harm will happen, especially in the fundamental theorem of calculus, where you subtract two values of the antiderivative and the constants will always cancel out. So you don't have to worry about those extra constants. That's a good thing. Now, the bad thing is that we don't use that, and you actually need it when if you ever take differential equations or even some problems in calculus 2, you will need that. So you kind of need to keep this at the back of your head, at the back of your mind, you know, oh, I probably need to remember that constant thing here, but you know, it's not so much used in practice in this part in calculus 1, so we have no reason to worry much about it. In fact, some instructors say, don't worry about that until you get to calculus 2. Well, I don't know. So maybe that's a good thing, maybe that's a bad thing. So I would say, well, here's an example where it matters what the constant is. If you want to match a function that has an initial value of 6 at 1, like this one here, and a certain derivative, a derivative means a certain type of tangents, then you wanna use that constant because that constant will be essential. All right, folks. So what I'm gonna do, I'm gonna stop recording here. I'm not gonna. Yes. So 1 second. Good question. So 1 second. 1 second, Nathan. So let me stop recording here. Oh. 1 second.